There are some new computing chips in town. Chips that combine high-speed processors like ARM cores with flexible FPGA fabric. These heterogeneous integrated processing platforms can deliver crazy amounts of processing power with a very small power budget. It's like the computing equivalent of a Prius-Ferrari combo or something. Ferraris? No. Ferrari. Yeah, that's good. Anyway, really fast and uses very little energy. But when do you need super fast computing? Yeah, that's right. When you're doing math. Hi, I'm Amelia Dalton, host of Chalk Talk, and today we want to talk about how to get all that math into your new SoC FPGA processor hip thingy. My guest today is Eric Cigan from the MathWorks, who, in my opinion, are the world champions of math. They have developed a process called model-based design that lets you take advantage of the math superpowers of MATLAB and Simulink and directly target the new hybrid chips, Xilinx Zynq and Altera SoC FPGAs. Before we get started, remember to click that link. There you can download a free tech packet that includes Xilinx Zynq support from Simulink, Altera SoC FPGA support from Embedded Coder, and programming Xilinx Zynq SoCs with MATLAB and Simulink training services. Welcome, Eric. Thank you so much for joining me today.
Happy to be here.
So why is the MathWorks getting into the business of supporting SoCs? What's the story here?
Well, it's really because two things. One is our customers have been asking for it, and second, our FPGA partners have been as well. We've got thousands of customers who have been using model-based design for processors, and now increasingly they're looking at these kinds of new devices as a way to address a number of their design challenges.
Sure. So these new devices came along and already use two things that you guys are really good at: hardware and software.
That's right. They really enjoy the fact that we can really help automate those flows. Let's look at one such example where people are asking us to use these model-based design.
Great.
One of them is motor control. We might think that as being a fairly boring sort of thing.
Maybe.
But actually a big part of the world's power is being spent driving motors, pumps, and that kind of thing. So it actually is quite relevant. What people are liking about this kind of platform, though, is the fact that they can use a very familiar process, and that is processor-based design. They have the ability to use a familiar programming model to reuse their legacy C code that they've been developing over the years.
Yeah.
Many of them like to be able to do floating point processing. That gets tougher in FPGAs, as you know.
Sure.
So being able to use the FPGA support on ARM processor is very powerful. And then finally, since it is a dual core after all, many customers have told us they want to be able to use one of the processors for user interfaces or for web interfaces, and they can do all that with the Cortex.
Very cool.
Now, additionally, you get the programming fabric here of the FPGA part. What customers are wanting to do with that is build high-speed peripherals that are customized. For those who are doing different types of networking, like in motor control, often in a factory floor setting, you need to support standards like EtherCAT or Profinet.
Yeah.
So those are available as IP from Xilinx and Altera and their partners. A lot of customers want to be able to do exotic signal processing or image processing as well.
Yeah.
And finally, because you can do a lot of things in parallel on an FPGA, that gives you scalability. So
Sure.
instead of controlling 1 or 2 motors, it could be 4, 8, 16. It's a very powerful platform because after all, motors run a lot slower than FPGAs do.
All right, Eric, tell me something. Why is this so hard to develop for this platform?
Well, the reason is because now you're taking what were a couple different distinct flows, embedded software development and FPGA design, and you're bringing them together.
Yeah.
Add into that the fact that you usually have somebody doing algorithm development, whether it's a control system designer, image processing engineer. You have those three roles coming to play, and they each are used to using their own tools in many cases.
So what kind of issues in particular do you see people facing on these types of designs?
It depends on your role. If you're the algorithm developer, you may be thinking, how can I hand off this intent to the downstream designers?
Yeah.
If I'm a software developer, I may be thinking, how can I interact with the hardware interfaces that are going to be in the FPGA part of the Zynq or the SoC?
Yeah.
And if I'm the FPGA designer, I may be thinking, okay, how can I interact with the software tasks they're happening on the ARM.
Sure.
But all three of them are wondering the same question, which is, it would really be nice if we had one environment where we could deal with this algorithm development as well as the embedded software development and the hardware design.
Absolutely. So I think I understand the issues at hand, but you keep talking about this model-based design. Tell me more about that.
Sure. So we think of it in three pieces. First of all, there's simulation. And what that means here is the ability to verify the operation of your algorithm before you've committed to hardware. A lot of our application engineers like to say, in simulation, you can break things 1,000,000 times and you don't cause any damage. And that's really important if you're talking about anything from a car engine to a motor. You want to be able to run in a benign simulation environment.
Yeah.
Once you've tried things out in simulation, you want to move on to prototyping. That's really the ultimate test, to be able to try out your algorithm running on a chip with the inputs and outputs that it's likely to encounter.
Yeah.
And then finally, you want the ability to be able to deploy on a target system. Unless you're doing some sort of paper study, you need to get this ultimately into an actual working system on a factory floor, on a road, or on an airplane.
Yeah.
That brings in a whole set of factors of being able to integrate with downstream production systems.
All right, Eric, this sounds great in the abstract, but how does this apply to actual devices from, say, Xilinx and Altera?
Sure. Well, let's just walk through the basic steps you'd have to go through in a model-based design workflow to target something like a Zynq device.
Perfect.
You start with simulation using MATLAB and Simulink for your algorithm development and proving it out with what becomes ultimately a test bench to represent the overall environment. You then proceed with your prototyping flow by first generating an IP core that is algorithmic HDL code that has wrappers in it that know how to talk across an AXI interface to an ARM core, or be able to talk to actual hardware through FPGA pins. Once you've built up that bit stream, then the next task is to actually load it onto your target platform.
Okay.
And then you move over to the software part of the task. That is generating the code, compiling it, building executable against embedded Linux, and then programming it into the prototyping system as well.
Okay.
Once you've done all that, now you want to be able to interact with it as an engineer and prove out your algorithm, try different test cases. And you do that by a process we have of real-time parameter tuning and processor in the loop interaction with the hardware.
Okay.
So that takes us through prototyping. Remember, that next step is getting to production. And the key thing there is we backtrack a little bit because we're not using the prototyping environment anymore. We are using, however, the algorithmic VHDL, Verilog, or C code that's being generated automatically out of Simulink.
Okay.
And once you have that code, you can then bring that into your production system where no doubt your production team is going to be able to integrate that using the FPGA vendor tools to create a complete application, complete implementation.
Okay, cool. So show me an example.
Sure. Let's start off with an example here. We call this one blinking LEDs.
Yes, the LED blinking light, the hardware equivalent of Hello World.
Yeah, you got me there. This is a pretty simple design. It's not going to be anything you'd actually build on a real Zynq or SoC.
Probably not.
But it's a pretty good example for us to work with. So let's go ahead and talk about that. What we see here is a pretty basic Simulink model, and we're going to go ahead and target, in this case, an Altera Cyclone 5 SoC. Let's talk a little bit about this model.
Okay.
We're going to try to make these 4 little lights, these little LEDs, blink that are on the corner of the development board. And the way we're going to do that is we're going to target to the ARM core some parameters, essentially, that are used to control the rate at which the LEDs are going to blink as they count up, or we're going to be able to change the direction as they count either up or down. So those high-level controls are going to be done through the ARM, and that's really cool because now we have the ability to control that when we actually go to prototyping.
Yeah.
So the other part we're targeting to the FPGA's actual guts of the counter itself. I'd like to show you a demo how that's going to work.
Let's go.
So let's go ahead and simulate that model that we were just showing a moment ago here.
Excellent.
So we'll go ahead and start by, we just hit the play button here. And that's just quickly building up the model, running it through the 300 steps here. And let's go ahead and look at the results here. We have 2 scopes here. This one is showing the LED output, so we're counting from 0 to 15. Remember, that's just 4 bits. And then we can look at the other output, which is the full 7 bits. Zoom that out so you can see this is a much smoother curve. So this is really showing up here what we're actually going to be getting on the real hardware when we actually run that.
Okay.
So now that we've proven this out with simulation, let's go ahead and build up that IP core. That was the first step we talked about in prototyping.
Okay, cool.
So we bring up a tool called HDL Workflow Advisor. Essentially, this is a cockpit for generating hardware.
Okay.
Once we have this started, we choose our target platform, the Cyclone 5 SoC kit. That sets up the whole downstream set of tools, Fortis, QSys, and so forth. And we'll go ahead and kick that off. Once we've actually chosen that, now what we need to do is set the target interfaces for our IP core.
Okay.
What we see here is the 4 ports that were part of our Simulink model, and now we can assign those to AXI or to IOs like the LED switches. So that's exactly what we can do in this panel. Tool automatically sets up, increments the addresses of the AXI interface. So that's all done automatically through automation here with Workflow Advisor. From this step on, actually, there's a lot that's going on. But we're going to go ahead and kick that off to get underway. We do things under the hood here, like checking the model and make sure it's compatible with HDL code generation. We help set up the HDL code generation to VHDL or Verilog, choose which reports we want to produce out of it. And here's just one such report that comes out of that workflow. This one is handy because it lets us look at some basic information, resource utilization, and that sort of thing. But it also lets us do things like browse through the generated HDL.
Cool.
So we can see the package, and let's get into the guts of the generated code, short though it is. And we can see the inputs and outputs of this IP core. As we scroll down farther, you can see some comments that have been stuck in there by the code generator. Here's ports, signals, and as we scroll farther down, we actually can see things that correspond to my Simulink model. So you see these green tags in here, they relate back to the Simulink model. We can click on them, and that will actually bring us right back to the Simulink model that corresponded to that. So that's going from code to model. We can also go from model to code by choosing a block and then navigating back to the C code.
Cool.
So this gives you this nice traceability that our customers like when they're worried about DO254 flows. That's a very attractive feature to many of our customers in high integrity applications.
Sure.
The next step is let's look at the IP core generation report. And this gives us a further level of detail. You could think of this as documentation in one single place for your IP core. So this gives you a lot of the ways that the code was generated, the parameters that were used to set it up. It gives us a couple table displays of the platform interface. It tells us about the AXI accessible registers for the IP core. And these are all in one single place so that when you go back later on and try to look at a core that's been generated by the algorithm developer, for instance, the hardware designer can get a good understanding of how to integrate that into a downstream flow. We also see we have this whole theory of operation guide that's generated on the fly. This talks about the architecture that's used. It also goes into more detail about how we synchronize between the processor and the IP core. Again, provides a lot of information all in one place that goes on beyond just the Simulink model that you started from. It has further information about the QSys environment in this case. If we were worried about a Zynq workflow, then it would be dealing with Vivado IPI, but it gives information about how we've integrated this core into the downstream environment.
Okay, Eric, now I know there's an ARM core in there somewhere. What about the software side?
That's right. So far what we've done is really focused on the IP core generation flow, but we've got more to get done here, right? So the next part is where we're actually going to generate the code, generate the interface models as well, compile that code and build it against Linux and target it into the actual hardware.
Okay.
So that's the next part of what we want to show. So what we're looking at now is this is the generated model that's going to be used to actually run this device on hardware.
Okay.
We're going to start by building code, C code, compiling that, and building up the executable. We'll go ahead and do that. First of all, though, because this isn't a simulation, it's real time, we want to run this indefinitely. So we're going to type in infinite here, running time. And we're going to go ahead and switch this over to external mode. That lets us control external hardware instead of simulating everything on our desktop machine here.
Okay.
Now we just hit the play button, and that goes ahead and it conducts all the tasks we need to do to build up the ARM executable. And what we're going to see here is actually a display of the board. We'll actually be able to see what's going on there and see if we're actually getting those LEDs to run. And you can see right now we have them all glowing blue. If we probe in here, we can get an idea of what's going on. It's counting very, very fast. Let's just do a little bit of cleanup here on the screen. Now we can see what's happening. It's counting extremely fast. That's why we don't really see anything going on. Remember, we have this controller, though. We can change the rate. We just have to tweak this slider bar, and we'll just slow it down a bit by bit here, and eventually, hopefully, actually see LEDs blinking. Starting to see that now as we reduce the rate slower and slower. And admittedly, this is a toy case, but if this were running actually some real algorithm that we cared about, we would have a lot of feedback right here at this point as to whether it's working or not.
Sure. We
can switch the direction of that as well here, so that's our other input into the system. By doing this, we get a lot of confidence in our simulation model as well as our algorithm ultimately.
So what kind of platforms do you support?
Okay, well, we have a set of them we support out of the box. As we saw before, we had the Cyclone 5 SoC development kit, also the Aero SoC kit, which is also a Cyclone 5 SoC device. From Xilinx, we have quite a larger number that are supported, starting with the ZC702, ZC706, Z-Board Community Board. That's a very popular one that we see out there a lot. We also have APIs so that customers can actually add their own custom boards, provided they use one of these supported devices. And one of our newest developments is a new kit. This is from Avnet, but it's a Zynq SDR board, and we have a very complete support for our overall SDR flow on this target, so we're very excited about that.
Okay, cool. So that gets us through simulation and prototyping, but what about production?
Yeah, we're not all the way there, are we?
No.
So let's go ahead and take it to that next step here. We start off with where we left off here. Remember, what we want to be able to do is to be able to generate algorithmic code and then to bring that into production environment.
Yeah.
The good thing about that is within the same workflow advisor, we can generate generic targets and produce IP cores that can then be used not just on this prototyping environment, but in a real production environment.
So Eric, I'm curious, how does this play with FPGA vendor tools?
That's right. Our customers demand us to work with the different tools that are out there. And so what we do is we generate projects for them. In this case, we're looking at QSys and Quartus 2 projects. We do the very same thing with Xilinx, with producing projects for Vivado as well.
Okay.
And then these are just a very natural handoff to the downstream tools.
All right, now I love blinking LEDs like the next guy, but what if I want to do something slightly more exciting?
Okay, well, we have a number of examples we ship with our software, but one of the more interesting ones we've been working on with our colleagues at Xilinx and Avnet is a field-oriented controller.
Cool.
This is a fairly complex motor control algorithm, but what we're including within this is all the work that goes into the algorithm, the DUT ultimately, as well as the actual physical models for the three-phase motor.
Okay.
And if we dig in one level below this, you can see what we have here are, we've color-coded these so that the blocks in C, like the mode scheduling and velocity control, we have those implemented on the ARM core. And then all the other blocks here that are in green, everything from doing basic conversions to different modes of control are running on the FPGA fabric. We also have models built into Simulink for all this that do things like deal with the encoder peripherals with PWMs. Those are all built up using Simulink and generated using our HDL and C code generation products.
All right, Eric, I think I'm ready to get started. Where would I go for more information?
Okay, well, we have a couple of different web pages that we use to make all this available. For Zynq, we have mathworks.com Zynq, and from this page, you can get at all sorts of resources, and you can actually download the support packages that enable you to do C code generation, HDL code generation. Once you've got our basic building block products, you can get the specific ones for targeting Zynq 7000 SoCs.
Cool.
We have a similar page for Altera SoCs. As with the other page, we've got videos, other links to documentation, all sorts of information here that will help customers learn in advance before they've actually started running this workflow on their own.
Great. Well, I think that's all I have time for today. Thank you so much for joining me, Eric. It was a pleasure speaking with you.
Happy to be on here.
Before we go, don't forget to click that link. There you can download a free tech packet that includes programming Xilinx Zynq SoCs with MATLAB and Simulink training services, Altera SoC FPGA support from Embedded Coder, and Xilinx Zynq support from Simulink. For Chalk Talks, I'm Amelia Dalton. For more Chalk Talks, check out the EE Journal YouTube channel or the on-demand section of eejournal.com.